All right, good morning, everyone. Welcome to our webinar, High Quality Recycling for Styrenic Polymers. Today, actually, I would like to share with you the secrets, quote unquote, how to make high quality styrenic polymers and why styrenic polymers excel excellently in the recycling field. Before I do that, let me share with you some information on our commitment to sustainability. So by innovation, by developments and other methods, we are aiming to save 1 million tons of carbon dioxide equivalents by 2030, and we are aiming to achieve net zero emissions by 2050. With respect to recycling, which is our topic today, we are aiming to sell 500,000 tons of so-called eco-products, which are mainly recycling products, by 2030. And actually, in order to have no impact on the regulatory compliance, we are guaranteeing actually 100% regulatory compliance with our products, be it eco or be it conventional. Let me start my webinar with a short overview on recycling technologies for styrenics. So basically, all of you know the typical classical mechanical recycling, and that will be the focus of today's meeting. Mechanical recycling collects post-consumer waste and sorts it and purifies it and recycles it into new polymers. And in an ideal case, the recycled polymers have the same properties as the post-consumer waste material, which are fed by original polymers. So no quality loss, but that's not trivial. And why that is not trivial and how we are going to resolve that, I will share with you in a few minutes. Another recycling route is depolymerization. Also here, styrenics have a head start because depolymerization means that by thermal or chemical treatment, in our case it's thermal treatment, at high temperatures, you can cleave the polymer chains from polystyrene into styrene, purify styrene, and polymerize them again to polystyrene or to copolymers of styrene. So that's a method which provides a high degree of freedom. This is a bit more ambitious from a technology point of view, but the degree of freedom and the broadness, the breadth of the applications are higher. Last but not least, by even increasing the temperatures further, we can pyrolyze polystyrene and other polymers in a so-called mixed waste or even tires into a feedstock which is consisting of small molecules. That means take plastics waste that cannot be recycled well by any other means, treat it, pyrolyze it, treat it at high temperatures, and convert it into small molecules that can be fed into the chemistry infrastructure. And that is actually a smart way to close the loop and to make the circular economy happen by taking waste that otherwise cannot be recycled and pyrolyze them into the feedstock and running over and over the cycle again. So after this overview, let me go straight into mechanical recycling, which provides a direct link from waste to polymers. So as I mentioned a minute ago, the municipality collections of waste provides mixed fractions that will be sorted and that will be converted into more or less clean fractions of polymers, for example, polystyrene, but also PET, polypropylene, polyethylene, and others. And that is a feedstock that is subjected to mechanical recycling and provides new polymers. The benefit of this mechanical recycling is low energy consumption, low greenhouse gas footprint. It uses existing technologies and assets and requires however, well-sorted waste. Over and all, we are aiming to stop landfilling, to stop incineration, and we'll do what we can in order to make this circular path happen. The topic of today is high quality recycling. What does that mean? So we actually have shown in projects that recycling of polystyrene, the mechanical recycling actually, can lead to a purity which is basically the same as so-called virgin polystyrene. So 99% and higher. And the result is that the recycled polystyrene is suitable for use in food contact application. It has by analytics the comparable quality as the original, again, quote unquote, virgin polymer. And that is an achievement that I think nobody of us could have imagined 20 years ago. And the way to achieve that is basically bales of polystyrene come out of sorting plants. Then these bales are sorted again by color, non-color. And as you know, that polystyrene typically is used in dairy product packaging with white color, let's say yogurt or whipped cream and things like that. Then sorting by color is an effective means to purify the polystyrene. It is followed by a hot washing step to remove traces of inks and so on, by an additional flake sorting step, and by the so-called super cleaning and eventually melt filtration. And what that means, I will share with you here. At this occasion, let me mention that the next slides stem from our recently published book, Recycling of Plastics, and here especially from a contribution, an actually original contribution from Herman van Roost, which is really recommendable to read. The so-called secret of achieving food quality starts with smart detection. When in a project, TOMRA sorting started their first tests to separate different styrenic polymers, all types and physical forms of polystyrene could be easily detected and separated by a combination of near-infrared and sorting technology. And it even appeared feasible, and you see that on this two-dimensional chromatogram on the left side, it even appeared feasible to separate high-impact polystyrene fractions by their rubber content, and even to distinguish them by the type of rubber used. And that's, of course, a great achievement, but this smart detection, and that leads me to the next slide, needs to be combined with deep sorting. What does that mean? So the sorted PS packaging waste is subjected to a screen to filter out the large part, to another near-infrared detection, and as a result of that, white high-impact polystyrene, respectively, high-impact polystyrene, polystyrene mixtures are achieved. And this is a self-learning system, actually, and continuously optimizing itself. And conservatively said, we will achieve white hips with larger than 95% food contact objects. Conservatively means, as I mentioned before, that in practice we have shown that we can even get much higher. The next part of the secret for achieving food quality is the washing step. Sounds simple, is, however, not trivial. For proper washing of polystyrene post-consumer flakes, the best results are actually obtained with the following combination of the so-called Sinner circle washing variables. Sinner was a chemist, an engineer employed by Henkel, and he developed this so-called circle where 4 variables are decisive for good purification. It's the time, the chemistry used, the temperature, and the mechanics applied. To start with mechanics, low friction is important. We need to avoid PS flakes breaking into small pieces, reducing the yield and the effectiveness of the subsequent flake sorting. We also need to look at the temperature. Temperature of around about 85 centigrade is high enough for thorough cleaning, but still sufficiently below the softening temperature of PS. If you would increase, then parts would clog together and agglomerate, and then the efficiency would go down. Another important part is to use caustic soda. In our experience, an aqueous roughly 3% concentration of this simple salt is okay, is sufficient. It allows the cleaning mixture to deal with the organic residues like paper, glues, and especially inks, and even to partly or fully dissolve the aluminum lids. And of course, we need a minimum residence time in order to finalize this purification. Last but not least, I mentioned this term super cleaning. Many of you know it. Just to remind, what is super cleaning? It's basically two families of super cleaning technologies that are typically in use. This is solid phase super cleaning and melt phase super cleaning. Solid phase super cleaning is used often when you have polymers that are partly crystalline, and the super cleaning temperature is above the glass transition temperature, but below the melting temperature of the polymer. Melt phase super cleaning you can use, for example, in polystyrene, where you have an amorphous polymer and where you need a temperature that is at or around the glass transition temperature or even above. Examples for such technologies are just really examples: Starlinger, Krones, NGR, Arima, and others. The key feature of a food quality recycle here is the removal of residuals, as I mentioned, above and or around the softening temperature, TG. Why is that? Because the glass transition temperature of polystyrene, let's say it's around 100 centigrades, entraps the ingredients, entraps even impurities, and prevents them from diffuse into food, what you see on the left part of this chart. That's a good property if you have an application with a use temperature which is well below the so-called glass transition temperature. For purification, you need to reach the glass transition temperature in order to free the ingredients, to mobilize the chain, and to allow, by a combination of temperature and vacuum, for example, to remove these ingredients and then to cool down the polymer again. So as a result, this process reduces the ingredients, the so-called cats and dogs, which we don't want to have, and retards the migration of residues into food. Now, this was a lot of theory and a lot of basics. Let me share with you that we are not staying as a company at these basic achievements. We are going further and announced a few days ago that EGN, TOMRA, and INEOS Styrolution are partnering in a, I can say, groundbreaking polystyrene food quality recycling project. Here, EGN will build a greenfield, state-of-the-art recycling facility with the capacity to process 40,000 tons of post-consumer polystyrene waste per year. EGN will manage the sorting and washing, while INEOS Styrolution will be responsible for the super cleaning purification process to comply with the strict requirements of the European Food Safety Authority, EFSA. An agreement with TOMRA to provide sorting technology and feedstock completes the project. TOMRA feedstock will collect the post-consumer polystyrene waste from disposed food packaging and deliver it to the new site in Krefeld in Germany. At this stage, another example of the styrenics industry aim to bring forward the use of recycled material into food contact, which is the highest requirements besides medical that you can imagine. Our industry association, Styrenic Circular Solutions, recently submitted the novel technology notification for recycled polystyrene as safe contact material. And that under the new EU regulation 2022-1616. What does that mean? With that submission, we are founding let's say, the process of allowing, in that case, so-called ABA structures to be used, officially used in food packaging. The ABA structure means we have on the outside, we have a cold extruded layer with so-called virgin polystyrene on the outside and recycled polystyrene on the inside. And as I mentioned in the slide before, the very unique property of polystyrene, namely high glass transition temperature, entraps the ingredients. It provides kind of a migration barrier in this ABA structure, and therefore we want to show that this is absolutely safe with respect to food contact and customer safety. After all that, you would ask, all right, very nice, sounds good, but where's the beef? You know, what is the effect of all that? I mean, it costs a lot of energy to recycle, to sort. Does it pay off, and is it really so good as it appears? And I can proudly say, yes, it is. We have done several life cycle analysis with renowned institutes to demonstrate the CO2 equivalent reduction of mechanical, but also chemical recycling of polystyrene. And compared to conventional HIPs, we could demonstrate that food contact mechanically recycled HIPs, with all these steps that you have seen before, achieves a 60% emission reduction versus the standard case. And I think this is very remarkable. And in addition, intrinsically, by recycling, we are reducing or avoiding landfill and emissions and incinerations, and we go the circular way. So with every new cycle, you have an additional positive effect. With that, let me share with you a few information on the second unique technology where I can say polystyrene is really made for recycling. And that is the depolymerization. Some of you might remember the K 2019 in Düsseldorf, where we for the first time demonstrated the closed loop of post-consumer recycled polystyrene back into yogurt beakers. And here's how it goes. So on the upper left, you see yogurt cups made of conventional polystyrene. These yogurt cups were flake sorted from household waste and subjected to a so-called depolymerization. And without going into details, I can say that depolymerization means a short but high temperature treatment of polystyrene where the polymer cleaves into monostyrene and some byproduct which requires some purification, distillation, and as a result you will get styrene. With this styrene, you can go into our production plant. You can polymerize it again and make polystyrene. And with this polystyrene, you can go to an extrusion manufacturer and make extruded sheet made of recycled polystyrene. And then you thermoform it, you fill it with, for example, in an FFS plant, you fill it with polystyrene, seal it, and then you make yogurt cups made of recycled polystyrene, ready to go this whole cycle again. So a very smart way. And let me say that just a few polymers can be depolymerized, polystyrene, PMMA, PET can be chemically depolymerized. So that's a method which is applicable only to a few of these big polymers. Also here, let me share with you the life cycle analysis that we made. And we compared the conventional polystyrene, GIPS, GPPS means general purpose polystyrene, with the recycled GPPS. You see here the emission reduction is a bit less. It's still remarkable 40%. It's a bit less than mechanical recycling, understandable because the high temperature and the distillation effort contributes to some energy consumption. But again, while considering the emission reduction of avoided incineration, then we achieve a total of 82% of emission or CO2 equivalent reduction. And again, also here, this is just the first part. Then we go the next cycle and the next cycle and so on and so on. So that means also this chemical recycling shows remarkable emission reduction effects and surely contributes to our aim to complete the circular economy. Now, I've talked a lot about polystyrene. In my last portion of this webinar, let me share with you some results on the post-consumer recycling of other styrenic polymers, for example, ABS. ABS stems from several sources. One prominent source is the so-called WEEE waste, the electrical and electronic equipment waste. And this is in conventional assets, shredded, and some ingredients like metals or flame retardant ABS or other polymers are removed by classical methods, sink flow, and so on and so forth. You'll find details also in the book that I recently mentioned. Washing is coming after that, flake sorting, and the high purity post-consumer ABS flake fraction is resulting. And with selected suppliers, which we collaborate, we were able to produce ABS, we call them Novodur Eco, Teleron Eco, with up to 70% of recycled content, which have properties which are in the typical range of ABS for industrial use. And some examples for the industrial use you find here. Just the example Novodur Eco and Novodur Eco High Heat. This is high-end recycled ABS for automotive. For example, B-pillars in the automotive sector can be made of post-consumer recycled Novodur Eco High Heat 160 MR30. And we have other grades also. And the nice thing is these products are so-called drop-in solutions with virgin polymer-like performance. And the mechanical recycling, as I have shown you in the case of polystyrene, and it's similar in ABS case, provides a significantly improved CO2 footprint. Not only the friendly black, but also gray, anthracite, and other colors are made. These are typical, let's say, especially in the automotive sector, typical colors which are in use, and we can cover them by the mechanically recycled Novodur. I mentioned that the life cycle analysis that we had performed in the polystyrene case, we did also with ABS, and here as an example, Novodur Eco. And you see very similar percentages. You see the Novodur Eco MR70, that means containing 70% of post-consumer recycled ABS, contributes to 57% of CO2 equivalent emission reduction compared to the original virgin Novodur. And I think this is equally remarkable. The Teleron Eco, just to complete this picture, shows a very similar effect. Right, with that, I think I'm at the end of this section. I hope you had a few insights, you had fun in listening. And yeah, together with my colleague Katja, let me open the Q&A session. Thanks very much for your attention. All right. So there were some questions in the chat. Let me see. The first question is, can you summarize again the fundamental requirements to make a polymer like polystyrene a material of choice for high quality recycling? Yeah, I think that is something I would be happy to do. So I mentioned that one fundamental requirement is the high glass transition temperature, which at use temperature provides an entrapping or entraps the ingredients, the remaining ingredients on a ppm or lower level that might migrate into food. So once you have a glassy state, then the chains are immobile, they don't move anymore, and they retard the migration of the, I call it cats and dogs, into the food. That's a very important thing. This is the case, just to complete this this picture with PET as well. PET, I think, has a TG of 70 centigrade, something like that, polystyrene of between 85 and 100. So if you stay in your use temperature below the glass transition temperature, then you have this this benefit. And another benefit, of course, is the easy detection. So you need to select out of the post-consumer mixed plastic waste those fractions which you're interested in, be it PET, be it PP, be it polystyrene, or something else. And the excellent detectability of polystyrene is for sure a key property. And yeah, last but not least, also the ability to super clean, to remove ingredients, to remove cats and dogs by temperature and vacuum is important to succeed in this high quality recycling. Right, I hope I could summarize this and answer this question properly. There is another question. What are the pros and cons of the different recycling methods for polystyrene? Yeah, that addresses the picture I've shown at the beginning, an overview of the different recycling methods. To make it short, I can say that mechanical recycling probably is the method which is most obvious, working as much as possible with existing assets and with some additional steps like super cleaning and purification, sorting and washing can provide an excellent or does provide an excellent basis for high quality recycled material. The next, let's say, recycling method is I would address here is depolymerization. This is a more fundamental change of the polymer. You degrade the polymer into its building blocks, and then you purify the building blocks and you add them again together to build long polymer chains. This is a bit more, let's say, ambitious in the recycling technology. It requires additional efforts, but the benefit is that you can create not only recycled polystyrene, you can use the styrene that you cleave in this process also for polymerizing fresh ABS, for example, or ASA, or styrene butadiene block copolymers. So that is basically what we can say about these two methods. And then last but not least, I mentioned the pyrolysis and the cleavage of the waste into small molecules. And this is especially important for me to mention because you all know the food packaging films, cheese packaging, other food products, fridged material, that typically are co-extruded film with 5, 6, 7, or even more layers. The one providing a barrier against oxygen, the other one a barrier against water, the third one is a compatibilizer, the fourth one is a seal peel layer, and so on and so forth. So you have 5, 6, 7 different polymers in these highly efficient packaging, which actually help to reduce the carbon footprint by extending the shelf life of food and making our modern life possible. But these co-extruded films cannot be delaminated anymore, and you need to treat them in recycling somehow. And a very smart way to recycle them is to subject them to a so-called pyrolysis. So you feed them into basically into an oven, into a reactor, heating up to 800, 900, let's say 1000 centigrades, and cleave the polymers not into styrene but into smaller molecules, C1, C2, and these molecules, they can be fed, as I mentioned in my webinar talk, into the chemistry infrastructure, and you can make all kind of products, plastics but also others, with this recycling method. So very smart and addressing an important fraction which otherwise could not be well recycled. So I hope I could answer well this question. There are several more. Let me pick one here: life cycle cost analysis. Not sure, it's just this. Can I go up? All right. Okay.
How does the CCA?
Yeah. I would let me address this life cycle cost analysis. I hope I understand this question correct. So what are the costs of life cycle analysis? I would say I can share with you. I have the requester here. I could share with you some data that we have. The life cycle analysis is a complex way. It goes according to ISO standards, of course, and working with renowned institutes indeed create costs which are in the, let's say, 5-digit range. But I can show you if you want. You can approach me after this webinar. I can share with you some more details. There is another question. Will it be possible to get these grades in natural colors? Yeah, that's actually a very good question, and I interpret it in the way that you are addressing both polystyrene and ABS. With polystyrene, I have to say we can provide white/natural color because we are focusing on the dairy product packaging, which typically, with just a few exemptions, are made in white. With ABS, admittedly, it's more difficult. ABS mostly appears in a friendly black, in dark colors, and it is we need to let's say color sort the feedstock in order to select the different color grades. That's possible, but as the major application of ABS is, for example, in electronic, household, and automotive, the typical colors there are dark, and so are then the colors of the recycled materials. So in order to answer the question, yes, it is possible, but not in an, let's say, unlimited volume, because we have to color sort the feedstock, for example, WEEE feedstock, which mostly appears in these dark colors. There is another one asking why depolymerization is used instead of pyrolysis in case of PS chemical recycling, better CO2 footprint. Yeah, that's also a very good question. The depolymerization actually is a gift by nature, right? As I mentioned before, not many polymers can be depolymerized into defined monomers, PMMA, PET, polystyrene, basically. And once you have that, then you don't want to cleave these products further if you don't need to. So if I have by feedstock relatively purified, high polystyrene containing material, post-consumer waste, then it would be smart to subject it to either mechanical recycling or to depolymerization. In depolymerization, it cleaves just into styrene and a few byproducts. Only if we have waste that is not really polystyrene only, it's mixed PET, polyester, polyethylene, polypropylene, and polystyrene and others, EVOH, polyamide, then it makes sense to do a pyrolysis, because then you cleave all these polymer chains into very small molecules which can be used for the whole chemical infrastructure. That means, to summarize, if you have the waste enriched in polystyrene, it would be smart to use mechanical or depolymerization technology. Then I see another question I have to ask my colleague. How much time would we have for answering the question? So 5-6 more minutes. That's great. Thank you very much. The question asks, what about the timeline of availability of the mechanical recycled grades? Yeah, that's a good question. I think I halfway answered them already in the talk. So you have seen that we recently announced this 40 kilotons per year project with TOMRA and ENG, and that is basically the timeline when we are aiming, and this will happen in the near future. So this will be a project where all participants are determined, and I cannot give you the exact date, but it will be driven forward, and we will offer the grades soon. Mechanically recycled grades we offer already today. As you have seen, we offer both polystyrene and ABS mechanical recycled grades. The high quality grades, which is the topic of today, we offer already today. The cream of the crop is the food equivalency. We can already demonstrate today that we achieve this food quality. We have a few, I would say, months ahead of us to demonstrate it in a large scale, and then we will be able to offer that. The ABS grades typically are not used for food. They are high quality in itself, but typically ABS is used for automotive E&E, and that is available today. And here, high quality I would define as an equivalency with respect to the relevant properties of ABS, which is aesthetics, which is mechanical properties. And I can say that already today, our mechanical recycled grades of ABS fulfill these requirements. They are as aesthetic as the so-called virgin grades. They are as tough as and stiff as the virgin grades. So here, you can buy them basically already today. Here is another question saying, if you get food contact approval for mechanical recycled polystyrene, why do you use in the middle layer only? Okay. So very good question again. These are two different projects. So the one is aiming for the ultimate solution, and that was key of my presentation today, so the direct food contact of recycled material. Again, a thing that was unthinkable 15, 20 years ago. Now it's in reach. Yeah, it will be available, and that is one project. The other project that we as a polystyrene producer pursued together with our peers and with partners along the whole polystyrene and styrenics value chain is this SCS, Styrenic Circular Solution project, on these ABA structures. So this contains say utmostly purified recycled material in the middle, plus virgin polymers on the outside. Both projects are independent, and both projects offer ways to close the loop. The ABA still works with some percentage of virgin on the outside. These are the A layers, and the ambitious project I focused on today actually goes for the, let's say, for the full effect, and aims to be in contact with the food coming from post-consumer recycling and purification process. Here's,
No, that's not.
I think, yeah, I have to stop now. Just get a note here. Let me share with you, maybe, Katja, you tell me how to go back. I need to to push this one. Thank you so much. And that is this one. Thank you. Yeah, thanks a lot. Right. There were more questions. I've seen a few more questions in the pipeline, which I could not answer because of the timeline. I wouldn't want to exceed the timeline too much, but please address all the questions and to me, or go to the INSTI webinars address at ineos.com. You also see two internet information links here that you can click on in order to get more information. But to make it easy, if you have any question, just approach me. I would be happy to contact my colleagues, the experts, and to bundle the answers and to feed them back to you. And at this stage, let me thank you again for your kind attention. Hope to see you soon in one of the next webinars, and have a great day. Thank you very much.
Driving success together.